Bioinformatics Micromodules, 3 problems related to hidden Markov models. In this module, we introduce 3 basic problems related to hidden Markov models and some corresponding definitions and probability rules required for describing the algorithms that solve these problems. We will focus on first-order hidden Markov models in these and coming modules. First, let's recap some basic concepts related to hidden Markov models. In a hidden Markov model, we have a number of hidden states, such as state A and state B in our example shown here. Each state has a corresponding initial probability, which is the probability that it is the first state in a sequence. After the initialization, every subsequent state depends on the previous state according to the transition probabilities. Each state is associated with emission probabilities that correspond to the probabilities of producing different possible observations, based on which an actual observation will be produced. In the run of the model, a sequence of observations are made, but the sequence of states that produce these observations cannot be observed directly. In order to discuss problems related to hidden Markov models mathematically, we need to introduce some symbols that correspond to the concepts we just reviewed. First, each possible state I is denoted by the symbol Si, and there are n possible states in total. Notice that we use S here since the word state starts with an S, such that the meaning of the symbols can be memorized easily. We use capital letter S to denote the whole set of state symbols, which is a convenient symbol to use when we do not want to write each Si separately. Next, we have the parameters of the model, which are the initial, transition, and emission probabilities. We use pi I to represent the initial probability for state I, and you can memorize the meaning of this symbol by remembering that initial probabilities are also called prior probabilities, and prior and pi sound somewhat similar. The probability for a transition from state I to state J is denoted as Pij. Finally, the probability for state I to emit observation O is denoted as EI bracket O. Again, we can use capital letter pi to denote the set of all initial probabilities, capital letter P to denote the set of all transition probabilities, and capital letter E to denote the set of all emission probabilities. Finally, we can use the symbol theta to denote the whole set of parameters of a hidden Markov model. Next, we have the hidden states. The state actually used in step T is denoted as Qt. Please be careful not to mix up S and Q. The symbol S is used to denote the possible state choices, while the symbol Q is used to represent the states actually chosen. Finally, for the observation in step T, we denote it as OT. Don't worry if you cannot remember all these symbols right away. We'll recap the meanings of them as we continue our discussion. You can also watch this part of the module again later for revision purpose. With the symbols introduced, we can now describe 3 basic problems related to hidden Markov models. The first problem is to compute the likelihood of a sequence of observations given the parameters of a hidden Markov model. Mathematically, this problem can be very easily written as probability of O given theta, where again O is the sequence of observations and theta is the whole set of parameters of the hidden Markov model. The simplicity of this mathematical problem definition explains why we had to introduce those capital letter symbols before. Please notice that in this problem, although we are given the model parameters, we do not know the state actually used in each step, and therefore conceptually, we need to consider all possible states in every step. We will come back to this point later in this module. The second problem related to hidden Markov models can be described as predicting the hidden states. Basically, given the parameters of a model and a sequence of observations, we want to know which state sequence is the most likely among all possible state sequences. Mathematically, we can state the problem in this way. This mathematical expression may look complicated to some of you, and so let's explain it bit by bit. First, the probability term probability of Q given O and theta is the probability of a state sequence Q given an observation sequence O and the model parameters theta. The max function with subscript Q means that we want to maximize the probability term among all possible state sequences. Finally, the ARG part means that after the maximization, we do not return the probability value as output, but rather return the Q that maximizes the probability as output. In summary, this problem is to find the state sequence Q that has the highest probability given the observation sequence and model parameters. In the first and second problems we just discussed, we assume that the values of the parameters of the hidden Markov model are given. How do we actually have these values in the first place? This is in fact the third problem, which is related to learning the values of the model parameters given some examples. Mathematically, given a set of observation sequences, which we denote as O superscript D, we want to find the model parameters such that the data likelihood is maximized. Please notice that each observation sequence is already composed of multiple observations, and here the training example involves D separate observation sequences, which explains why we have the superscript D part in the symbol. To study the three problems, we need to have some basic knowledge in probability. In fact, we do not need anything difficult, but just three basic rules. The first rule is that the joint probability of two variables x and y can be computed by multiplying the unconditional probability of x and the conditional probability of y given x. To see what it means, suppose x is whether it will rain tomorrow, and y is whether the temperature will drop tomorrow. Suppose unconditionally, there is a 20% chance that it will rain tomorrow, and given that it will rain, there is a 60% chance that the temperature will drop. Then the probability that tomorrow it will both rain and have a temperature drop is simply 0.2 times 0.6, which is 0.12. Here, we use the standard convention that a capital letter denotes a variable and a small letter denotes a possible value of it. In our example, capital letter X is the binary variable of raining tomorrow, and it has two possible values, namely true and false. We can write specific values in the formulas when it makes the explanation clearer. The second rule is the law of total probability, which states that if we have the joint probability terms of x and y, and we sum up the terms for a fixed value of x across all possible values of y, we get the unconditional probability of that value of x. For example, suppose we fix the value of the raining variable to true and consider all possible values of the temperature drop variable. The sum of these terms is the unconditional probability that it will rain tomorrow. Finally, the third rule is the Bayes rule, which states that probability of x given y is equal to probability of y given x times probability of x divided by probability of y when probability of y is not zero. This rule may look complicated, but if we multiply both sides by probability of y, we get probability x given y times probability of y on the left-hand side, and probability of y given x times probability of x on the right-hand side, which are of course equal due to the first rule we just studied. That proves the Bayes rule. We should also note that if there are additional variables whose values are always given, we can just keep them as conditions in all the terms. For example, here variable z is always a given condition, and therefore we can use Bayes' rule to turn the expression on the left-hand side into the one on the right-hand side, just like the case without this extra condition of z. Before we move on, let's briefly discuss how these three probability rules are to be used. Essentially, when we solve the problems related to hidden Markov models, we often encounter probability terms that cannot be computed directly. When that happens, we apply one of these three rules to turn the expression into another expression. We do it repeatedly as long as we have terms that cannot be computed directly until every expression left in our formula can be computed directly. Let's use the second problem to illustrate what we just discussed. As a reminder, the problem that we want to solve is this one, which involves the probability of state sequence Q given observation sequence O and model parameters theta. We cannot directly compute probability of Q given O and theta, but we can easily compute probability of O given Q and theta, since it is just the product of emission probabilities, as we will see later. And therefore, we use Bayes' rule to convert the original expression to the three terms on the right-hand side. Notice that the term probability of O given theta is a constant for different values of Q, since it does not involve Q. And therefore, in order to maximize probability of Q given O and theta, we only need to maximize the product of the first two terms on the right-hand side, and the term in the denominator can be completely ignored. Our next question is how we can find the state sequence Q that maximizes the product of the two terms. A brute force way is to simply try all possible state sequences. To illustrate, suppose we have played the coin flipping game and get tail, head, tail as the sequence of observations. Suppose also that we are given the parameters of the hidden Markov model as shown. Now, since the observation sequence has three observations, the state sequence also has three states, and thus we need to try all possible sequences of three states. Given that each time there are two possible states, namely coin A and coin B, we have 2 to the power 3, that means 8 possible state sequences, as shown in the first column of this table. For each of these 8 possible state sequences, we need to compute the corresponding values of the two probability terms indicated in the second and third columns. The first term, probability of O given Q and theta, is the probability of the observation sequence given the state sequence and model parameters, which is simply the product of emission probabilities. The second term, probability of Q given theta, is the probability of the state sequence given the model parameters, which is simply the product of initial and transition probabilities. Finally, multiplying these two terms together, we get the values in the last column of the table. Then by comparing these values in the different rows, we find that the value in row 5 is largest, which means the state sequence of BAA has the highest probability given the observation sequence of tail, head, tail, and the model parameters. Notice that we can only compare the probabilities of different possible state sequences, but we cannot tell for sure which one was actually used to generate the observation sequence. This is another example with the observation sequence changed to head, head, head. The corresponding table of computations is as shown. And by comparing the values in the last column of different rows, we find that the state sequence of AAA has the highest probability. You're encouraged to do the calculations on your own and see if you come up with the same conclusion. Before we end this module, let's analyze the amount of calculations required if we solve the problem in the brute force way that we just described. First, for each possible state sequence Q, we need to compute the product of M emission probabilities, where M is the number of observations, 1 initial probability, and n-1 transition probabilities. This means in total, we need to compute the product of two m terms, which is linear with respect to the length of the observation sequence. On the other hand, the number of possible state sequences is exponential with respect to the number of observations. For instance, if we had 10 coin flips instead of 3, our table would have 2 to the power 10, that means 1024 rows instead. This exponential growth of the number of table rows is too expensive. Then how can we get the answer using less time? If you have looked at the table carefully, you would have noticed that a lot of calculations are repeatedly done many times, leading to wasted efforts. Therefore, one idea is to reuse partial results, shedding the light of using dynamic programming. We will explain how dynamic programming can be used to solve the problems efficiently in the next module, which is the third and last goal that we described in the last module.